Coming to you live from the math department. Pre-calculus math 11. Dots. 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 Today, chapter 4, Quadratic Equations, section 4.1, Graphical Solutions of Quadratic Equations. So we looked at the problem in class of the rectangular garden measuring 3 meters by 5 meters, and the length and the width meant to be increased in a way such that the overall area is tripled. And we want to find what the new dimensions of this garden will be. Well, until you draw this out, I'm not really sure that you've actually started this question. So we have this garden with both length and width being increased by the same amount, so that this length here is equivalent in length to what's being added on over here. And we could call this any variable value that we like. Sometimes I like to use L for extra length or W for extra width. In this case, since we're doing it to both, why don't we just call it X, and we're going to declare that X is the amount by which both the length and the width are increased. Now originally the area here was 3 by 5 or 15 square meters, but we're going to be tripling that area, which gives us the following. Since we know that the area is increasing up to a value of 45, we can take this equation and set it equal to 45. What am I looking for in this? Well, I'm looking for the values of x such that x squared plus 8x plus 15 is equal to 45 square meters. Now I could guess and check my way to a solution, which is a valid method, if not potentially time-consuming, tedious, and sometimes misleading in terms of the result that you get. So how else could we solve this? Well, if you think about Math 10, we learned how to solve systems of equations by graphing. And what if I considered this as two separate equations? What if I looked at this as y equals 45 and y equals x squared plus 8x plus 15? I could graph both of these equations and try to find the place where they intersect on the graph. Whether I'm using Desmos or my TI-84, I can go ahead and input these values. You can see that whether I'm using Desmos or the TI-84, I need to adjust the window settings to get my y maximum up to something greater than 45, and then I need to find the intersections of these two equations. Now I get two solutions here, one of which I must reject. The negative solution doesn't make any sense. Only the positive one works. X equals 2.782. So my side lengths of 3 plus x and 5 plus x are going to be 5.782 and 8.782. Now we could have done this slightly differently by simplifying this equation first. Since 45 is equal to x squared plus 8x plus 15, I could have rearranged this as 0 is equal to x squared plus 8x plus 15 minus 45 and tidied that up to simply x squared plus 8x minus 30. Now I could graph this one equation here. In this case, when I graph it, instead of finding where it has a value of 45, all I need to find is where does this equation have a value of 0. In other words, I just need to find its x-intercepts. These locations, the x-intercepts of a quadratic function, are called its zeros. And notice that on the grapher, they occur at the same x value as the intersection points when we did two separate equations. As usual, I don't really care whether you want to do this as two separate equations where you're finding the intersection, or if you'd rather do it as one equation and find the zeros of that equation. Personally, I would do one equation and find the zeros, but it really doesn't matter. Your results will be the same. Now, a little bit of terminology just to make sure we all understand. When we talk about the x-intercepts of a quadratic function, The x-intercepts are also known as the zeros. Those terms are virtually interchangeable. And the solutions to a quadratic equation, in other words, what value of x, or the variable, makes the whole equation true, the solution, those are also known as the roots. And now it's time for two for you. The first one, solve this equation by graphing. And in the second one, the flight path of a soccer ball kicked by Graham can be modeled using this function, where h is the height of the ball in meters and d is the number of meters away from him horizontally, so that h of 2 means the height of the ball when it's 2 meters ahead from where Graham is standing. Use your grapher to determine the total horizontal distance when the ball hits the ground and when it's at its maximum height. Well, that's all for today. Thanks for dropping in and learning a thing or two with me about how to solve quadratic equations by graphing. I know I sure had a lot of fun, and I bet you did too. So until next time, keep your pencils sharp, your batteries charged, and I'll see you in class. Is it nap time yet?